All right, let's run through this stuff real quick. Um, so first off, as far as the topics on the exam, 9.3, which is hypothesis tests and possibly a confidence interval for the difference between two population proportions. So that's going to be stuff like this. Um, and in fact, maybe we should just do a quick problem like that. So right here, problem 11. In 2007, 144,796 students took the AP Biology exam, 84,000, so on and so on of them were female. The same year, this many students took the AP Calculus exam, and of those, that many were female. Is there enough evidence to show? And so, okay, this phrase, is there enough evidence to show? What follows is our alternate hypothesis. So, okay, what are we curious about? If the proportion of female students taking the AP Biology exam is higher than the proportion of female students taking the AP Calculus exam. So that's quite a mouthful. I don't want to say that every single time. So I'm going to say that P1 is the proportion of students, proportion of, I suppose, female students taking the AP Bio exam. I'll just say in bio. And P2, same idea, but this is in calc. Right? And so now what is the alternate hypothesis using the notation P1 and P2? So my alternate hypothesis, my H1, is that P1 is higher than P2. My null hypothesis, it's not stated, but implicitly it's that they're the same. It's that P1 is equal to P2. Okay, so as far as stating the hypothesis goes, that's this. Although technically, if I only write, where is it? If I only write this stuff, it doesn't make sense without telling the audience what is P1 and P2. So they kind of go together, right? Okay. Um, Now if I were to enter all this in the calculator, I should have, here's one, great. Let's go stat, tests, and we had two proportions that we're doing a test on. So it's the two prop test. And in fact, it's all in here because I did this in yesterday's class. So I'm just entering, let me get a side-by-side going. So we have the total number of students who took AP Bio, that's my N1, and then the amount of them that were female. And then the same thing for calc, right? And so the amount that are female is the X1 and X2, respectively, and the total number of students in the class is N1 and N2, respectively. The alternate hypothesis, it's that P1 is bigger than P2, so I selected that one. And now we can go ahead and calculate. And here we go. And there's a lot of P's that show up on this screen. The first P is the P value. So what's different about that P? It doesn't have a hat, right? Everything that has a hat, it's talking about a proportion. In fact, it's talking about a sample proportion. The P1 hat equals 0.58. That's saying that in AP Bio, 58% of the students who took the exam were female, whereas in AP Calc, 48% were female. So that's what that stuff is saying. Okay, so what is the probability? Well, it's zero. That so okay, what does this mean? So when it computes this probability, it's the calculator, what always happens is it assumes that the null hypothesis is true. So it's going to assume that the same ratio of female students are in AP Bio as in AP Calc. And if that's true, then by random chance, what are the odds that in fact we are this far apart, where in AP Bio it's 58% and in AP Calc it's 48%. And in fact, the probability of being that far apart when you're supposed to be the same is zero. Okay. Um, so that's what's going on with this screen. And okay, so zero, that's less than alpha, no matter what alpha is, because alpha is always positive. In this case, alpha is 0.05. That's our significance level. So we reject the null hypothesis, right? Under this assumption, we should not get what we got. So I guess we shouldn't make that assumption, right? Okay, so that's the idea. That's a possible test question type of thing that'll show up. Okay, what else can show up? So I'm going to look at the goodness of fit stuff next. I guess all the chi-squared stuff. So chi-squared is when you have categorical data. So categorical data, stuff like this. So I'll just get the calculator off. Psychologist wants to determine whether the five main stress release activities people use after work are not equally popular. A random sample of adults is surveyed and the following data is collected at the 5% significance level. Okay, so why do I underline that? Anytime you see something talk about significance level, that's talking about doing a hypothesis test. So this is sort of the catchphrase that's going to show up in all the hypothesis test questions. And it means that when you select something from your stat menu over in tests, it needs to have the word test in it, right? So we can see it has test, has test, has test, but some things have interval or some things have int in the name. Don't use something with int in the name unless the problem says confidence interval or confidence level, right? The problem needs to say confidence in order to use that. Um, when the problem says significance level, it's talking about a hypothesis test. Okay, so can it be concluded? So just like over here, how there was that little jingle, is there enough evidence to show? The other little jingle, that's the signal that we're about to look at the alternate hypothesis is, can it be concluded? Okay, can what be concluded? Can it be concluded that there's a preference among the five activities, i.e. that they are not all equally likely? So H1 is that not all activities are equally likely. Okay, the null hypothesis, and this is true for every single chi-squared. Well, I guess, okay, I should just say, what is this? This is a goodness of fit test. So for every goodness of fit test, the null hypothesis is that your observations match your expectations. And so sometimes they will tell you exactly what they expect for every category. And other times, like in this problem, what they're hinting at is that being equally likely is what we're testing. So we're going to assume that they are equally likely. The null hypothesis, the thing that's going to go in the background, is that all activities are equally likely. Oops, likely. I.e., the probability you're going to exercise is the same as the probability you're going to meditate, is the same as the probability you're going to watch TV, and so on and so on. And our textbook doesn't like to use subscripts with names. It's like I just wrote PEX for probability exercise. What our textbook likes to do is just say P1. The probability being in the first category, which is the exercise category, is the same as being in the second category, which is the meditation, and so on, until the fifth category, which is reading. Now, there are five categories. If they're all equally likely, they all have a chance of 1/5. Okay, fine. All right. If you total up all those numbers, all these numbers, sorry, then your sample size is 110. So anyway, we've stated our hypotheses. How do we know this is a goodness of fit test? Well, goodness of fit test always has this kind of look to it. We're going out, we're collecting and seeing how much, what do we observe for each different category? And it'll just kind of fit on a single row or a single column. Where's my lazy one? Here's another lazy goodness of fit. And I said that it'll always fit on a single row or a single column. And you might look at this and say, there's two rows or columns. In this case, there's two columns, right? But observed is the data. Here in this problem, they're telling you what we expect, and it's not equally likely. So equally likely, man, my spelling. So we'll look at problem 12 next. Let's go ahead and finish up problem 10. Okay, so we have a goodness of fit test. So what do we need to do for a goodness of fit test? Also, the textbook's not bad. Like, if this seems a little chaotic because I'm just focusing on the exam review, peek at chapter 10 of the textbook, peek at the goodness of fit, and just kind of see if it clarifies anything for you. Come on. What's happening here? Those are all working. There we go. There we go. All right, cool. Um, oops, not what I want. Stat, test, goodness of fit. So it's way down here. Option D. Fine, there we go. Okay, it wants our observations in the list L1 are expected in L2. And so just to say what we expect, so our sample size is 110. I get that by adding up all those numbers, okay? And we expect 1/5 to be in every single category. 1/5 of 110, let me redo this. 1/5 of 110 is 22. 1/5 of 100 is 20. 1/5 of 10 is 2. 1/5 of 110 is 22. So if we, whoop, whoop, where to go here? All my observations are in list L1. So that's the 30, 22, and so on and so on. And in L2, I put my expectations. I expect exactly 1/5 of 110 to be in every single category. That's what's in there. Go back to stat, back to this. It was option D. Can I do that quickly? Alpha D, there we go. All right, degrees of freedom. That's one less than the number of categories. Here there were 5 categories. 1, 2, 3, 4, 5. So the degrees of freedom is 4. So we're going to calculate, and here we have our probability. So the p-value is 0.17. I'll just say 9. Who cares? Oh, I suppose I should make it 180, whatever. Regardless, this is bigger than our significance level, bigger than alpha, so we fail to reject. Okay, fine. So the evidence is not strong enough that it's not equally likely, right? So we expected everything to have 22 people in it, but that allows for some fluctuation just because of random chance. And we're not far enough away in those fluctuations to change our mind. We continue to believe the null hypothesis, which is that all of these are equally likely. Okay, that's what's going on here. Let's take a look at problem 12. So suppose you have the following observations and expectations. Let's put this in the calculator. So what do we observe? 16, 18, 3, 17, 14. So technically, well, I guess it has to do with our expectations. So, you know, I'm not even going to bring it up. Or whatever, I'll say it as I enter it. In order for us to use a goodness fit test, every category in the expected amount needs to be at least 5. Like we should expect to get at least 5 observations. Our observed can be under 5 because that's what actually happens in the messy, messy real world. But each of these numbers have to be at least 5 in order for the stats, for the mathematics machinery behind it to kind of work out. That was in the assumptions of the chapter. We don't really test you on that. Anyway, okay. I have observed and I have expected put in the calculator. Let's go back to the stat menu, go to test, go to goodness of fit. We have all that. How many categories are there? 1, 2, 3, 4, 5. Okay, so my degrees of freedom is still 4 because it's 1 less than my number of categories. Calculates, what's the p-value? It's 0.399, good enough. And so we fail to reject. Fail to reject. Okay. I'm being really lazy. I did this. What would A look like? What's the hypothesis? So the null hypothesis is that expectations model reality. Okay, I'm being kind of lazy. Oh, the thing is, on Alex, we tend to state this in terms of probabilities, and I don't want to have to convert this to probabilities. If I had to, we won't make you do this, but if I had to, I should add up everything here. So what is that? That's 14 plus 16 plus 8 plus 18 plus 12, 68. And I would say the default hypothesis, the null hypothesis, is that the probability that you're in this first row is 14 out of 68, which you could just write as 14 out of 68. That's fine. The probability in the second row is 16 out of 68. and so on and so on. You would just list the expected proportions, okay? Expected probabilities. And you say, that's my null hypothesis. That's what I expect to get. The alternative hypothesis, we want to know, um, can you conclude the distribution has changed? Is that the probabilities do not follow that distribution. It's that some or all of the P sub I, so like P1, P2, P3, right, are different. Okay, so what do these null and alternate hypothesis have in common with these, right? Well, the null hypothesis, the H0, so in this case, it's all activities are equally likely. Don't look at the sentence and words, look over here. The null hypothesis specifies the proportions you expect to get. That's true in both cases, right? In the first thing, in problem 10, they were all 1/5. It's equally likely. In problem 12, they're not equally likely, but we can still specify them. 14 out of 68, 16 out of 68, and so on, right? The alternate hypothesis is that the distributions differ. So not being equally likely is what it looks like for 10, and just saying they differ is what it looks like for 12. But it's always specified for the null, differs for the alternate. That's what a goodness of fit is, okay? So that's why a goodness of fit always just has this like one row or column of data. You're just looking, hey, does this fit what I expect? Or does it differ? How good do it fit? Okay, goodness of fit. All right. Whereas, so something like this, there's no expectation versus observation type of thing. This is just a regular chi-squared test. And for a regular chi-squared, you're always going to have like a data table. You're going to have multiple columns and multiple rows. And you're checking to see if the variables that index your rows, so these variables, I'll say var1, even though it could be var2, it doesn't matter, influence these variables, var2. Does your major influence the probability that you'll do online versus in-person classes, right? So that's the idea for a chi-squared. It checks what's called independence. Independence, my God. For two variables to be independent means they don't influence one another, right? So it seems plausible that your major could influence your propensity, your probability of taking online or in-person classes. So, okay, if you ought to do a chi-squared, so laws, we want to go to matrix, which is this button here. Thankfully, nothing happened because it tries to do an inverse, but we can't do an inverse on this screen. It's this button here, but I want to get to the matrix menu, so I have to do second and then that button. Now I'm in the matrix menu. Go over to edit, and I need to input this data. So how big is this data? It's 3 rows and 2 columns. And if you ever forget what's what, I mean, the moment you hit enter, you'll see if your matrix size agrees, right? And then you can kind of change those entries as needed. So, okay, I have 45, 55, 30, 70, 60, 40. Great. It's all in. Now I go to stat, go to tests, chi-squared test. And now that's pretty much all we have to input for chi-squared. This expected in the B, the calculator computes that. What it computes is if these two variables were independent, then what's the distribution you would expect to get? Okay, that's what the calculator does behind the scenes, and it will store that in matrix B. What we input is just matrix A. So we're done. We've done it. Hit calculate. Here we go. So the p-value is 0.123126. So how did I get that? Well, what it originally reported was 1.126 e minus 4. And this e minus 4 means this decimal right here needs to move 4 places to the left. So it went 1, 2, 3, 4, and then you cushion with zeros. Okay. So very low probability, we are going to reject H naught, which I never stated, so I should probably state those. So the default hypothesis, H naught, is that the two things are independent. So your major is independent from class format, like that you signed up for or whatever, right? The alternate hypothesis is that they're not independent. Not independent. I'm being very lazy here. We should probably put it as a complete sentence. Independent. So how would I do that? I would say your major and the class format you sign up for are not independent, right? I'm just too lazy to write that. This is how the null and alternate hypothesis will always, 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 always look for a chi-squared test. This is what a chi-squared test is testing. It's looking to see if the two variables are independent or not. So your null hypothesis, you just say the two variables, major, class format, and you say they're independent. That's the null. Variable 1 is independent from variable 2. The alternate hypothesis is always variable 1 is not independent from variable 2. That's it. That's a chi-squared test. That's what the calculator is able to do. All right, fine. So that problem's done. Do we have any other chi-squared problems? No, this looks like, what's kind of interval? Okay, we could look at that later maybe. Okay, I think that's it. All right, cool. So far we've seen this kind of stuff. We've seen this kind of stuff. Goodness of it, you'll just have one row or column of data. Chi-squared, you're going to have a matrix of data, but you're looking at how the two variables influence each other. And then we get to the chapter 11 stuff, which had to do with best fit lines. So the notation for the best fit line. So, all right, you might have a scatter plot of some data. Okay. And then, so there's the data, the sample data. And based on that sample, you get the sample, my God, best fit line. Now, I say best fit. It goes by many names. It can also be called the least squares regression line. Fine, whatever. But that's this. Okay. Now, this is just your sample and the data. The actual population, this is what we don't know, but maybe the true population, right? Maybe it looks like this. I don't know, whatever, okay? And it has this like slightly different kind of line, whatever. But that's the difference between these two things. And so there's what line actually models the population versus what line models our sample, okay? And then beyond that, use context clues. So this thing in front of X is the slope, okay? All right, I say all that because every exam that we've had has notation questions. And something that the exam might ask is, what's the correct statistical notation for the population linear model slope? Okay. Linear model is just talking about a best fit line, a regression line, a least squares line. These are all names for the same idea. Okay. And they want to know what's its slope. Okay, so population level, linear model, slope. Population level, linear model, slope, it's beta 1. Okay. Beta 1. All right. Anyway, you can work through these. Some say sample, some say population, and then y-intercept versus a slope. So, okay, we'll come back to those kinds of things. We need to know what we're going to do here. Not that, not that. Okay, let's look at problem 14. Okay, researcher wants to determine whether there's a linear relationship. So whether there is, so does it exist? Okay, a linear relationship between the number of hours students spend studying and their exam score. So let's go ahead and put this in the calculator. So how many hours did they study? 0.5, 1, 1.2, 2, 2, 2.5, 1.5, 3. Great. What was their exam score? 65, 70, 72, 74, 85, 90, 75, 100. Cool. So now tests. We want to know, is there a linear relationship? So we're going to test. So there's test in the name if there is a linear relationship, but also this will have a significance level, right? All these hypothesis test questions have a significance level. All right, so here we go. So our X variable is how many hours they study. Our Y variable is their score. That's terrible penmanship. Our Y variable is their score. That's all there. We go down here. What is the null hypothesis? We assume, oh no, sorry. The null hypothesis is always the same. What is the null hypothesis for every linear regression test? It's that the slope is 0. Okay, but how do we say slope? In the calculator, it's just beta. So that's why in this screen over here, way on the left, it has beta. Okay, so the slope equals 0. The calculator will think of that as beta equals 0. That's the null hypothesis, which we don't need to teach the calculator because that's the same null hypothesis for every linreg t-test, okay, which is the name. If you look at the top of the calculator screen, it says linreg t-test. This is what the calculator is going to kind of assume behind the screens as a null hypothesis. What we teach the calculator is the alternate hypothesis. So in this case, we just want to know if there is a linear relationship. So if the slope is non-zero. So we just want to know this. If instead the problem said whether, so I'm going to look here, starting at whether. So whether there is a positive linear relationship, then I would choose this one. It would have a positive slope. If it wants to know if there's a negative linear relationship, I choose this one. It has a negative slope. But here we just want to know, is there a linear relationship? So it's non-zero. Okay, calculate. Here we go. So what's our p-value? It's 4.05 e to the minus 4. So what does that mean? It's 1, 2, 3, 405. Okay. Right, I had to move that over 4 places. Okay, so we're definitely going to reject H naught. What's H naught? It's that there is no linear relationship. It's the slope is 0, right? It does look like there's an influence. If you study, you'll get a higher exam score, that kind of thing. Okay, so that's part A. Part A is us doing this hypothesis test and using the p-value and saying, okay, we're going to reject the null hypothesis. Now we're going to use the best fit line. So in part B, what is your best guess, right? So we're going to use the best fit line at the score of a student who doesn't study at all. Okay, so if you don't study at all, that means X is equal to 0 because X is how many hours you spend studying. So if I look at my calculator screen up at the top, it says Y equals A plus BX. And then I scroll down and it says A is 55.76. And maybe I should make that 77 and round to 2 decimal places. Plus, and then B is 13.49. Okay, and then I should put an X. Okay, so that's my best fit line. If X is 0, if the student doesn't study at all, my best guess for their score is 55.77. Okay. All right. What would your best fit line predict for the score after studying 10 hours? So I'm going to plug in 10 for X, and that's going to move the decimal over 1, basically. So I would have 55.77 plus 134.9, and I don't know what that is. 55.77 plus 134.9. they're going to get 190.67%, which is obviously impossible. The most you can get is 100%. And this is also kind of the point of this. You might see this kind of question on a test where they want you to put down what you get, but they also want you to know, like when we do these predictions and these models, there's limitations, right? And so they're kind of trying to hint at that with this kind of question. So, all right, that is how that looks. And just to show you, so previously when I said the alternate hypothesis might say something different, it might ask whether there's a positive linear relationship. Let's just do that really quickly. So in tests, so I've already input this data in L1 and L2. I go to my linreg t-test. The only thing that changes is my alternate hypothesis. I'm going to test for a positive slope. And just notice what happens. It's still the same A and B value. You still get the same best fit line because the best fit line is determined by the data, and the data is the same. So those A and B values, they're the same. Just look at the probability, the P value, right? It's even lower, right? In fact, it's half of what it used to be. Okay, now we have 2e to the negative 4 instead of 4e to the negative 4. And we don't need to get into the weeds as far as like why that is. But the point is, what I want you to know and observe from this is that if you change your alternate hypothesis, it changes your p-value. And since this data strongly supports a positive relationship, like that sort of shows up by what's going on here. And we have this p-value being lower is stronger evidence for a positive relationship. A low p-value is strong evidence to reject the null hypothesis, to accept the alternate. I'm not supposed to say accept, I'm just supposed to say reject, but whatever. So let's look at problem 8 now to kind of emphasize that kind of stuff and what's going on. So the whole point of problem 8 is just to kind of notice how p-values, test statistics, and rejecting the null hypothesis all sort of work together. So here's the thing. When I look at this, I look at the alternate hypothesis or even just the null hypothesis, and I see this beta, right? It doesn't really matter, but this is a linreg t-test. They're checking for slope, and in this problem, null hypothesis is that the slope is 0, there's no linear relationship, and the alternate is a positive linear relationship. Excuse me. So what I want you to notice in this alternate is we're checking for positive. You're checking for beta 1 being bigger than something. This symbol here tells us that this is a right-tailed test, okay? And so stronger evidence against the null hypothesis. So strong evidence against the null hypothesis is the same as having a low p-value, right? A low p-value means a very low probability that the null hypothesis is true, okay? Which you could think of as a high probability it's not true, right? It's evidence against the null hypothesis. So, and that corresponds with test statistics, test stats in the tailed direction. Okay, so what I mean, I have two numbers, 1.5 and 1.9. Which of these two numbers lies more to the right on the number line? And I look right because this is right-tailed, right? So I have 1.5. Why is my stylus not writing? Oh my God. And 1.9. And so that one is stronger evidence against the null hypothesis, which is to say it has a lower p-value, right? Low p-values is evidence against the null hypothesis. So you can imagine different ways to phrase this question where it's the same answer, right? So instead of saying which test statistic is associated with a lower p-value, I could say which test statistic is stronger evidence against H naught. It means the same thing, right? Okay, let's look at B. This symbol is telling us this is left-tailed. So I look at these two values. That one lies more to the left, which means that one has a lower p-value. If this problem were to say which one has a higher p-value, then the answer would be that one, right? So look at the way the alternate hypothesis is telling us this hypothesis test work. Is it left-tailed or right-tailed? Moving left lowers the p-value. Moving right increases the p-value. Moving in the direction of the tail decreases the p-value. Moving against that direction increases it. The other thing to keep in mind is that with any of these problems, instead of asking which one has a lower p-value, I could have asked which one is stronger evidence against H naught. It would be the same question using different wording, right? I should have done that. I should have done that in like these ones, but I didn't. I just copy and pasted. Sorry. So if we look at C, this is also left-tailed, and this number lies more to the left. So this number has a lower p-value. Okay, what's going on here? So yeah, you could look at this symbol and say it's left-tailed. Technically, just to be safe, you want to look at the object P1 minus P2. So in this case, in order to get P1 minus P2, let's do this. P1 less than P2. I have to subtract P2 from both sides, and I get P1 minus P2 is less than 0. So you want a number, and then you want the thing you're looking at, okay? And then you can say, oh, okay, I'm moving left. This is left-tailed. This number lies more to the left. That one has a lower p-value, okay? Because imagine, still looking at this, imagine if it said P2 less than P1. Well, oh wait, no, how do I want to do this? Yeah, I guess I'll just do that. That's fine. Well, this symbol is still the less than sign, but the object that I care about is P1 minus P2. So in order to make that appear, I subtract P2 from both sides. And when I subtract P2 from the left, I get 0, P2 minus P2. When I subtract it from the right, I get P1 minus P2. And now we can see, oh, the thing I care about lies to the right of 0. So then that would be a right-tailed test, right? So just, don't just look at the inequality. You want to create P1 minus P2, you might have to move something over. Or if you need to create mu1 minus mu2. But it's always going to be thing 1 minus thing 2. Whether it's a mu or a p, I don't care. Okay, but that's what we want to look at. And then that should be bigger or less than 0. Okay. And then you can figure out which tailed direction there is. Okay. I'm getting lazy. You can sort of look at those. Summarize what's happening above. If a hypothesis test is left or right-tailed, then the test statistic further left or right, respectively, so you have to move in the same direction, is stronger evidence against H naught. Lower p-values means we are more likely to reject H naught. Lower p-values means H1 has stronger evidence, right? So being able to understand this whole interplay is kind of nice. Okay, so let's talk a little bit about correlation coefficient. That's this R thing. R is between +1 and -1. So the sign of R, meaning whether R is positive or negative, agrees with the sign of the slope. So we have a positive slope, we have a negative slope. So R would be positive, R would be negative. If you don't obviously see a line, R would be 0. Okay. So if we had to arrange some figures based on their R value, well, I'm looking at a positive number, a negative number, and a 0. So I guess the negative number, then the 0, then the positive number. So that's how I would arrange these figures based on R value. I don't know if my little thing is in the way. Okay. One of these, I think I ask you to just summarize the correlation coefficient. Not there. Oh well. Yeah, well, I got to wrap this up and get to campus. Um, all right, let's just do this last problem. So it very explicitly says confidence interval. I haven't read this yet, but I know when I go to my calculator, I'm going to choose something with INT or interval in the name. Okay, a survey found that a sample of this many urban residents, 310, said they regularly use public transportation. Ah, that's a proportion. It's an X1 out of an N1. It's a, how many positive for something compared to a total. It's a proportion. Okay. And then out of a sample this many rural residents, this many said they use public transit. Constructed 95% confidence interval for the difference between the population proportions. All right, fine, let's do that. Stat, edit. Okay, so I need an interval in the name, and this has two proportions. Hey, look, 2 prop z int. That's the one we want. I have two proportions. I want a confidence interval. There we go. What is x1? It's 310 out of 1250. Eh, sorry. X1 is 310, N1 is 1250, X2 is 176, N2 is 1100. 95% is what we want. Go ahead and calculate that. And what do we get? We get 0.05571, 0.12029. There we go. I don't care about any of that. Fine. All right, what is the point estimate? The point estimate is always, always, always the center of the interval. So what is the center of these two numbers? Does the calculator just give it to me? Let's see, let's see. The calculator does not. Well, it kind of does. So if I do, I'm looking at P1 hat minus P2 hat. That's going to be the center. And so what is that? That's 0.248 minus 0.16. And 24 minus 16 would get me 8, so 0.088. And that seems believable. It's, about 3.5 bigger than that, about 3.5 smaller than that. So, okay, technically about 0.035 bigger, 0.0, whatever. Okay. Did I do that right? Yeah, that looks good. So anyway, that's my point estimate for this. Well, okay, I misspoke. Those two things are equal. This is my point estimate for P1 minus P2, no hats. Okay, so I go out and take a sample. The difference in sample proportions, difference in sample proportions. So urban ridership compared to rural ridership, okay, is 8%, almost 9%, okay? But that's not my entire urban population and my entire rural population. So I'm estimating that. Anyway, my point estimate is this. Was the interpretation? We're 95% sure that somewhere between, 5 point, I'm just going to call that 5.5. We'll just call that that. We are 95% confident that the difference in proportions is between 0.055 and 0.120. Okay, just say that for an interpretation. We're 95% confidence that the difference in proportions, because we're trying to estimate a difference in proportions, right? So the thing we're looking for, we're 95% confident it's in this specified interval. Like just say it in words. Okay, that's all I'm doing today. So cool, cool, cool. Stop share and end.